Hello everybody. We'll solve one more example on the using steam tables to solve energy band problems on units on process units. So the problem that we have is about a boiler. So we have two feed streams of water, one at 120 kilograms per minute. This is the flow rate, and it's saturated liquid water at 30 degrees Celsius. The second is 175 kilograms per minute of saturated liquid water at 65 degrees Celsius. And um, the product pressure, we have only one outlet stream which has a pressure of 17 bars absolute. And of course, a boiler is a unit that is used to boil water, and the name is very clear. So heat is provided for the boiler in order to increase the enthalpy of the water and turn it into steam. So the steam that we have is comes out of the boiler at or through a pipe that is has 6 centimeter ID. ID is the inner diameter of the pipe. Now this is the diameter where the fluid is flowing in. So when we want to calculate or do any calculations regarding the flow rate, regarding the velocity, and anything regarding the flow of fluid in a pipe, we use the inner diameter for this. We need to calculate the heat, the amount of heat that we need to provide in kilojoules per minute. Given that the effluent stream is saturated steam at the boiling pressure, so it's saturated steam, we will neglect the kinetic energy. It's not the changing kinetic energy. This needs to be clear. We neglect the kinetic energy of the liquid inlet streams. So these are the information that we know, what we have. So the first thing we will do is to draw the flow sheet. We have two inlet streams. We put the saturated liquid, we put the flow rates, the temperatures, we put the saturated steam, flow rate, and the pressure, and the inner diameter. So we have all the information. Also we have here the Q, the heat that is provided to the unit. Now we want to calculate the Q. So to calculate Q, the first thing we said is if we have some missing flow rates, we can do mass balance. So we don't have M3. So to calculate M3, we can simply do simple mass balance. We have two inlet streams of water and one outlet stream of steam. So simple, very simple mass balance, we can get the mass flow rate of the product, which is the sum of these two flow rates. It's going to be 295. Now we can write the energy balance equation for open systems, and we can cancel some terms. So we have nothing or no information about the potential energy. So we will assume that the change in potential energy is 0. We don't have, or we have information about the kinetic energy, that the kinetic energy of the feed is neglected, which means that the change in kinetic energy, so we consider the kinetic energy of these two streams is 0. So the kinetic energy is going to be only this. So this minus 0 is the kinetic energy of the stream. So the kinetic energy is the change in kinetic energy, or the change in kinetic energy is the kinetic energy of stream 3. And for the heater, there is no work. It's just a unit that is used to boil water. So there is no work included here. So the work is 0. So you'll end up with just 3 terms: the enthalpy change, kinetic energy change, and Q. And if we write it in more details, the Q is going to be the delta H plus delta kinetic energy, and the delta H is H out minus H in. H out is the enthalpy of this stream, it's only one stream, and the H in is the enthalpy of these two streams, which is 2 streams. So this is why we have it as M3H3 hat minus the summation of M1H1 hat plus M2H2 hat. And what we need to do now is to find the 3 H's, H1, H2, and H3, and the change in kinetic energy. The flow rates are already known, so we don't need to worry about them. So if we calculate want to calculate the kinetic energy change, we said it's the kinetic energy of the outlet stream. So this is the kinetic energy of the stream. We know the kinetic energy of the outlet stream is going to be half mu square, and this is half m3 u3 power 2. u3 is it's not given, but we are given the inner diameter. So this is one relation that we know from fluid mechanics, and this is something that we can just know by simple observation, that the velocity is the volumetric flow rate over the cross-sectional area. This is in meter cubes per minute or per second. This is in meter square, so the division of these two is the velocity in meters per second. So this is a very, very famous relation in fluid mechanics. We use it a lot. So the volumetric flow rate, we don't know the volumetric flow rate, we know the mass flow rate. So we can say that the volumetric flow rate is the mass flow rate multiplied by the specific volume. This is kilogram per what units per minute, and this is in kilojoules per kilogram. So this the multiplication of these two will give us the volumetric flow rate. The volumetric flow rate, I mean the specific volume is already available in the tables. We have the pressure of 17 bars. So if you go to the steam table, I don't know if this is clear here or not, but if you go to the steam table, this is pressure of 17 bar. It is saturated steam, so this is going to be the specific volume in meter cubes per kilogram, and we can find this value. For the area, it is the cross-sectional area, which is half or pi over 4d square or pi r square, whatever what you like to do. Pi over 4 d square, pi over 4 multiplied by the inner diameter. The inner diameter is given to be 6 centimeters, so we'll put it in 0.06 to be in meters. So we have the cross-sectional area in meter square. Again, the specific volume is 0.1166, which is this number. And we know the area from the previous step, and we know the mass flow rate, so everything would be calculated here. It's going to be in meter cubes per minute, and we can multiply by 1/60 to convert this into meter cubes per second. So you know the volumetric flow rate. Now we can take this value, substitute here to get the I think there's something wrong here. This is meter, not meter cube. I'm sorry, this is a mistake. So this is meter, not meter cube. We already divided by the area. So this is the velocity in meters per second. So you can take this velocity and use it to calculate the kinetic energy change, which is the kinetic energy of stream 3. So this is going to be in joules per minute. In 6.06 times 10 power 6 kilojoules per minute, which can be in joules per minute to make the number a little smaller. Of course, the value of the kinetic energy is very high because the velocity is very, very high. 200 meter per second is a very high value for velocity. Anyways, so this is the kinetic energy. For the enthalpy, it's going to be just picking numbers from the tables. So we know that this is saturated liquid water at 120 degrees Celsius. I mean at 30 degrees Celsius. So we'll go to the table, find 30 degrees Celsius. The enthalpy of saturated liquid water is 225.7. So this is the first enthalpy. The second enthalpy is at 65. We know the enthalpy is at 64 and 66. So for these two enthalpies, I can, of course, it's liquid water, so it's 267.9 and 276.2. So it's going to be in between. So we can do interpolation, and we'll find the value to be 272.05, which is an average value between these two numbers. So this is the enthalpies of the feed streams, H1 and H2. Now H3 is going to be very easy. We have 17 bars. This is saturated steam. So this is going to be the value. Let's get closer. So this is 2,793 kilojoules per kilogram. So this is the enthalpy of the product stream. Now we have all the numbers, so we can directly substitute in the energy balance equation. And here we have the numbers. This is the enthalpy of the product. This is the enthalpy of the feed, the second feed, and this is the kinetic energy. And now we have the Q as 7.67 times 10 power 5 kilojoules per minute. There is one important observation that we have to notice here. That the value of the heat, despite having very high kinetic energy in this problem, we agree that this is a very, very high velocity. The enthalpy change is 100 times the more than 100 times the kinetic energy change, which means that still what we mentioned before about the effect of or about the value of kinetic and potential energy compared to the Q and work and enthalpy is still valid, even in a case where we have very high velocity like this. Still the enthalpy is the dominant term, and if you check this number and this number, they are almost the same. It's the second decimal place that is affected, which is a very small number that can be neglected. So again, this confirms what we mentioned before about the small values of kinetic energy and potential energy. So this is the last example that we will solve here in this chapter. Next chapter or next video, inshallah, we will talk about the start the next chapter, which is about calculating the enthalpies in case we are dealing with anything else other than steam, or using material that we don't have any tabulated data for. So we'll start it next time, and I'll see you then, inshallah. Goodbye.